All right, ladies and gentlemen, today we are going to talk about properties of definite integrals. Much like derivatives, there are properties that allow us to manipulate, add, subtract, multiply, divide things as we go through problems. And you're going to find that the vast majority of these are the same as derivatives. I'm going to jump right into this so that we don't have too much time on this video, as this is kind of an add-on thing. A couple of these you have already identified and you've already used. For instance, the zero length interval is when my interval of points, my limits of integration are the same thing, which means there is zero width, meaning there can only be a zero area. Likewise, you've also revealed that if I take an interval and if I give you that the b is greater than the a, that if I work backwards from a large number to a small number, then all I really need to do is find the integral from a to b of f of x dx, and it will be the negative. Again, some of that stems from the idea that we are doing a negative change in x, therefore leading to a negative integral value. The next ones are very similar to derivatives, nothing new here. They are that if I have a constant multiple, I can actually factor the constant multiple out of my definite integral, leaving me to find just the f of x with the k on the outside. The other one that's similar to derivatives is the sum and difference, in which if I have the integral of a sum or difference, I can take the definite integral of one of the functions and add or subtract from that the definite integral of the second function. The only one that will be new is this fourth line, where we are going to deal with some value c in between a and b, and the only reason why this is slightly different is because, so as I was saying, as we go through here, there's going to be this limit integration, and we're going to have a point in between, so I can actually take the integral from a to c of f of x dx and add to that the integral from c to b of f of x dx. Bam! Now what we can do is we can utilize those properties. Oh, before I get too far, I apologize. Please make good note of this. Just like a multiplication and division in derivatives, there is no, you do not just distribute the integral across products and quotients. That will not work. That leads to the following set of questions. I give you some information. I tell you that the integral from 0 to 3 of f of x dx is 4, and the integral from 3 to 7 of f of x dx is 1. If I look at those intervals, I recognize on the first question that 0 to 3 and 3 to 7 is really just the entirety of 0 to 7. So this integral can be rewritten as the sum of the individual pieces put together, which means this is really just 4 minus 1, which is 3. Likewise, with a constant, as stated above, we can factor that out. The integral from 3 to 7 is negative 1, so that is just 2 times negative 1, which is negative 2. If you'd like to pause here and try out the other 4 before I put them up, you may certainly do so. If you've paused, then great. Otherwise, for C, your answer should be 0, since the limits of integration are the same. And you probably skipped straight to E, so I'll do that, where if I look at this, I can actually rewrite this as the negative 1/2 of the integral from 0 to 7 of f of x dx. You'll notice I did 2 steps here. I took the negative of the integral since I flipped the limits of integration. I also factored out the 1/2. The integral from 0 to 7 I calculated in a, so this is negative 1/2 times 3, or negative 3/2. The only two that may possibly be difficult are d and f. What I can do here is I can recognize this as the integral from 0 to 3 of f of x dx plus the integral from 0 to 3 of 4 dx. I could choose to factor this out and call this 4 times the integral from 0 to 3 of dx, but that kind of gets confusing. What I like to do is I'll look at it this way. The integral from 0 to 3 is a simple one. That's 4. But then this maybe messes with us. So let's imagine what this graph looks like. My f of x is 4. So if I graph that, and if I look at this function between the endpoints of 0 and 3, you can see I simply make a rectangle with a height of 4 and a length of 3, which means this has an area of 12, giving me a final answer of 16. Likewise, I can do the same thing here, where I'm taking the integral from 0 to 7 of f of x dx minus the integral from 0 to 7 of 2 dx. And I can recognize that this integral from up here is 3 minus 2 times now a distance of 7 is going to give me 14, which will give me negative 11. Now these are not the only things that we'll utilize as properties to assist us. We're also going to look at the idea of evens and odd functions. Remember, an even function from pre-cal says that an even function can be defined as a function that is reflected over the y-axis. If that's the case, and I take an integral from some negative a to some positive a, then what I can recognize is that's really just taking this integral right here. And since it's a reflection, this integral will be the exact same amount. So all I have to do is double the integral from 0 to a of f of x dx to get the integral from negative a to positive a. For instance, if I look down here, if I go from 0 to 5, f of x dx, and that's 3, since I have this integral from negative 5 to 5, and I'm dealing with an even function, we say the answer would be 6, 2 times 3. Likewise, if I know that this function is even, if I go from 0 to 3, and that's positive 3, then from negative 5 to 0, this will also be a positive 3. And if I take this, all I would do is multiply the 4 out to get 4 times whatever my answer from a is, and get 24. Likewise, we have odd functions. Odd functions are, of course, going to be functions that are reflected over the y equals x line. We say they have origin symmetry. And much like even functions, if I'm between some negative a and a value, the area below the curve will actually be equal to the area above the curve. It's going to be the nature of odd functions, which means that if I take an integral from negative a to a of f of x dx, I should get 0. Using the same situation as on the left, for an odd function, a is always going to be 0, which means c, by nature, also has to be 0. The only one that might mess with us is b. But if I'm an odd function, I know from 0 to 5 is 3, so from negative 5 to 0 should just be the opposite, since it will be below the x-axis, leaving me with a negative 3. Now these particular skills are all going to kind of embed themselves into the following questions, where we're going to have to connect things and do all sorts of neat connect concepts. So when I take a look at that, I take a look at the first problem, and it says f of x is odd, and the integral from negative 4 to 7 is 5. So what do I have? I have a function that I know from negative 4 all the way out to 7. This odd function has a net change, has an integral that will equal 5. That whole thing together equals 5. I want to know what the integral is from 4 to 7. So I'd like to find this piece. So what I can do is I can recognize that if I look at my integral from negative 4 to 7 f of x dx, I'd like to maybe split this up. I could go from negative 4 to 4, and in fact that becomes extremely useful. Because this is an odd function, I know that this area above here cancels this area below, which means that that has a net area of 0. I want to go from negative 4 to 7, so I need to take the integral from 4 to 7, and this happens to be even more serendipitous because that's what I'm looking for. And if this is 0, then I know that 5 has to be my integral from 4 to 7 f of x dx. Likewise, if I look at the next question here, I have an even function, so I would draw an even function. I do find drawing these to be useful. It says from -2 to 2 has a positive 4, so it's an even function. We should be reflections. And more importantly, from here to here, this is -2 to 2, we're also going to go from -5 to 5. So I don't know, maybe it does something like this. And I would like to find the integral from 2 to 5. So I take a look at this, and one of the things that I can note is I actually, from these, because these are even functions, if my integral from -2 to 2 is 4, then I know my integral from 0 to 2 of f of x dx should be 2. Likewise, if my integral from 0 to 5 to 5, -5 to 5 is 12, then my integral from 0 to 5 of f of x dx will be 6. Well, the 0 to 5 would be the entire range from here to here. So what I could do is I could take this, and I could break up the integral from 0 to 5 f of x dx into the integral from 0 to 2 f of x dx plus the integral from 2 to 5 f of x dx, which gives me the interval that I'm looking for, and I know values for 0 to 5 and for the next piece. We can say that that will equal 4. I will give you a moment to pause the video and try out the bottom two questions. All right, if you had a chance to see if you did these right, let's take a look. In this next one, it says the integral from -5 to 2 of f of x dx is -17. I don't see any evens or odds, so I'm not going to be able to use that ability up there. It gives me some intervals, and the first thing I notice is that this -5 to 5 pretty much contains everything I want here. If I want to take the integral from -5 to 5 of f of x dx, what I really need to do is I need to take the integral from -5 to 2 f of x dx plus the integral from 2 to 5 f of x dx. So I'm looking for this integral. I know what this is. This is -5 to 2 is -17. And I have to be careful here. Because what I may do is I may look at this and say, well, okay, from 2 to 5 is -4 and move on. But if I look, this integral is actually the reverse of what I've written. So I need to recognize that since that's the reverse, I need to take the negative of my answer, which is +4. And -17 plus 4 is -13, which is my final answer. And last but certainly not least, if I have an integral from 0 to 3 f of x dx equals 8, I can take this problem and I can split this from 2 to 5 of f of x plus 2, f of x minus 2. Make sure we reverse. Oh, waiting for the computer to catch up. Plus the integral from 2 to 5 of 2x minus 1. Now, you'll see that in this problem, I actually left it 2x minus 1. I could have called it the integral of 2x, and I could have called it the integral of 1. But 2x minus 1 doesn't scare me too much. And from our formative yesterday, we should recognize that this can actually be drawn. -1 comes up like this, and I want to be between 2 and 5. And if I evaluate those heights, that'll be a height of 3 and a height of 9, which means we have a trapezoid that I can evaluate. So if I were to calculate out that area, that would be 9 plus 3 over 2 times the distance between, which is 3. So that's 12, that's 18 here. And then I've got that nasty thing. Now this goes back to the first day we talked. You'll notice that this is really just a shift right of the original function I was given. And you'll also notice the limits of integration are also a shift right in the same quantity, which means that I should maintain the same area. There was no vertical or anything like that to mess with this. So this will turn out to be 8, and 8 plus 18 is 26. Ladies and gentlemen, I hope that this was not a terrible thing. I'll take a look at the questions that pertain to this, but I felt like this is a pretty straightforward lesson that we can work through with some speed, so it wasn't anything I was too terrified of. I hope you have a great rest of your break, and I look forward to seeing you when we get back.